Good morning, good afternoon, and good evening, everyone, wherever you are. Welcome to this plenary talk. My name is Thomas Liu. I'm an A-star senior fellow and also a faculty member of the Electrical and Computer Engineering Department of NUS. I'll be your moderator this morning. Today, our plenary talk will be on the new quantum metric system, the reform of the International Systems of Unit, or what we commonly call SI. As a member of the International Committee of Weight and Measure, I had the privilege and honor to participate in the 26th CGPM, or General Conference of Weight and Measure, where this reform was voted in by more than 60 countries from around the world. So it's my pleasure and also honor to introduce our distinguished speaker today, Professor William Daniel Phillips. Professor William Daniel Phillips is from the National Institute of Standards and Technology in the US, as well as the University of Maryland. He's the founding member of the NIST Laser Cooling and Trapping Group, as well as also the Joint Quantum Institute at the University of Maryland, which is a cooperative research unit with NIST. Professor Phillips have a long list of achievements in laser cooling and cold experiments, including the first electromagnetic trapping of neutral atoms, and also some surprising thing that he has done, like cooling, atoms down to a million of an absolute zero, which is very amazing and also surprising. Things in confinement of atom in optical lattices. His group has also worked on Bose-Einstein condensation. Of course, the result of his work is realized in atomic fountain clocks, which are the primary standards for the world timekeeping. And currently, the focus of his research is in the area of ultra-cold atoms for quantum information. So you can see, in a sense, that Professor Phillips is an extraordinary magician in a way, in harnessing the laws of nature. He is widely honored and recognized. He's a fellow of the American Physical Society, a fellow of the American Association for Advancement of Science, and also the American Academy, fellow of the American Academy of Arts and Sciences. He's a fellow and honorary member of the Optical Society of America. He's also a member of the National Academy of Sciences, the member of the Pontifical Academy of Sciences, and a corresponding member of the Mexican Academy of Sciences. And of course, all of you know, he was awarded the 1997 Physics Nobel Prize for the development of methods to cool and trap atoms with laser light. So without further ado, let us welcome Professor William Phillips to this plenary talk.
Thank you very much, Thomas, for that kind introduction. Okay, so as you heard, we're going to be talking about the revolutionary reform of the metric system. And as you also heard, I'm from the Joint Quantum Institute and the National Institute of Standards and Technology. And I'm part of the Laser Cooling and Trapping Group. And it's a pleasure for me to work on a daily basis with Gretchen Campbell, Paulette Trey Porto, Ian Spielman, Ida Tietzinger, and Charles Clark. So, the French Revolution, among other things, it brought us the metric system. And what I'm going to be talking about today is the continuation of that revolutionary idea of a new system of units. The dream of these French revolutionaries was to have a system of measurement that was good for all time, for all peoples, à tous les temps, à tous les peuples. And this medal that was cast to commemorate this idea shows this mythological creature measuring the earth. And in fact, that was exactly what they attempted to do. Their new standard of length measure was based on the size of the Earth. And they sent out surveyors to measure the distance along this meridian from the northern part of France, Dunkirk, down to Barcelona in Spain. And from there, they were able to extrapolate the full size of this meridian, and they defined a meter to be 1/10,000,000th of the distance between the pole and the equator. But almost as soon as they had come up with that definition, they found that it was not very convenient. And so they did what people had done historically for many years. They created an artifact, a metal bar in this case, and the distance between two scratches on this metal bar was the definition of the meter, not just for France, but eventually for the entire world. But almost as soon as this meter bar was made, sometime shortly after 1875, it was clear to people that they could measure length much more accurately using the interference of light. And this photograph here shows an interferogram of light beams interfering, where this central dark spot could change to a bright spot by changing the displacement of a mirror by just a fraction of the wavelength of light, which was much smaller than the ability to determine where these scratches were on this metal bar. And so eventually the definition of the meter was changed to be the wavelength of light coming from some sort of a discharge lamp. But almost as soon as they made that new definition, people realized that lasers had much better qualities. The light coming from a laser was much more pure than the light coming from a discharge lamp. And so the question was what to do about that. Should they redefine the meter again in terms of the wavelength of the laser? Well, they did not do that. They did something far more brilliant. They defined the speed of light. In 1983, the definition of the meter was changed to be the length of path traveled by light during a time interval of a certain fraction of a second. What this effectively does is to define the speed of light. And because of this relationship, that the wavelength of light is equal to the speed of light divided by its frequency, it meant that if you could measure the frequency of light, now that you have defined the speed of light, then you know exactly what the wavelength is, and you can use that as your meter stick. So this was wonderful. It was the kind of definition that did not need to be revisited when people made better lasers or when people made better techniques to measure the frequency of light. And people did both of those things. This definition was still perfectly good for all time, the kind of dream that the French revolutionaries had. And the modern metric system now has all of the base units: the kilogram, the meter, the second, the ampere, the Kelvin, the mole, and the candela. All of these, which are the base units on which all other measurements are based, has each of these base units defined in the beautiful way that the meter was defined, by fixing the value of a constant of nature. In the case of the meter, it was the speed of light, and in the case of the other base units, well, we shall see. This new definition of the International System of Units, the SI for Système International, took place on the 20th of May, 2019, the anniversary of the International Treaty of the Meter in 1875 that established the metric system as the standard of measurement for the entire world. And this was, I'm claiming, the greatest revolution in measurement since the French Revolution. And one of the main motivations was that the definition of the kilogram was a mess. We desperately needed a reform in the definition of the kilogram. Why is that? Well, the old definition before the 20th of May of 2019 was that the kilogram is equal to the mass of the international prototype of the kilogram, an artifact. Here's a picture of it. Inside 3 different glass bell jars is a small cylinder made of platinum iridium. It was made shortly after the 1875 International Treaty of the Meter, and it was made to match the mass of the kilogram of the archives, which was installed in 1799. So this little piece of metal here, which weighs by definition 1 kilogram, was styled after an artifact that was made in response to the development of the metric system at the end of the 18th century. Now, the problem is that in spite of great care, keeping this kilogram very clean and cleaning it according to a very delicate procedure, it appears that the mass of the international prototype of the kilogram is changing. Of course, that's an intolerable thing because it's supposed to be the standard of mass. So what do I mean when I say it appears to be changing? Well, this graph shows a comparison of a number of different copies of the kilogram, copies that were made to be, as much as was possible, identical to the international prototype of the kilogram. And over a span of more than a century, these copies of the kilogram were compared to that 1 kilogram that was chosen to represent the international prototype of the kilogram. And you can see that almost all of these copies are increasing in mass. Well, it's not an unreasonable conclusion to think that what's really happening is that the international prototype of the kilogram is in fact losing mass. But that's impossible, because by definition, whatever the international prototype of the kilogram is, it is, by definition, 1 kilogram. Now, that's a very, very difficult situation. We have an artifact that was made in the 19th century based on an artifact that was made in the 18th century, telling us what we mean by mass in the 21st century. And so we need to make a change, and the decision was made to change it in the same way that the definition of the meter was changed. In other words, by defining a constant of nature. Well, what is that constant of nature? Well, in order to understand that, let's remember what I'm pretty sure is the most famous equation in history. E equals mc squared. What does that mean? It means that the total energy of an object at rest is equal to its mass times the square of the speed of light. Now, let's think of another equation, not quite as famous as this one. This tells us that the energy of a photon, a particle of light, is equal to Planck's constant times the frequency of the light. Now, if we combine these 2 equations together, setting these 2 equations equal to each other and solving for the mass, we find that the mass is equal to Planck's constant times the frequency divided by the square of the speed of light. What does this equation mean? What it means is that the mass of a photon, and I put mass in quotation marks here, and you'll see why in a moment, is equal to Planck's constant times the frequency of that photon divided by the speed of light. Well, what does it mean to say the mass of a photon? What it means is that if I had an object, let's say a radioactive nucleus, that emitted a photon in the form of a gamma ray, and I could measure the frequency of that gamma ray and plug it into this equation, then this equation would tell me how much the mass of that nucleus changed. That's what we mean by this equation. And the reason I've gone through this exercise and written this equation this way is because this tells us, in principle at least, how we can relate mass to Planck's constant. But the fact of the matter is, that's not the way we're going to do it in practice. We're not going to weigh photons. In principle, we could. And in fact, people do, but they just don't do it well enough for us to use it as a standard of mass that has the same kind of quality that the old definition of mass had, the one that was based on the international prototype of the kilogram. Instead, we can still use the definition of Planck's constant, and a device, an electromechanical device known as a Kibble balance or a Watt balance, invented by this gentleman, Brian Kibble, in order to realize the definition, in order to bring into reality the definition of the kilogram based on a chosen value for Planck's constant. And this movie will show, I hope, how that works. So let me start the movie. Okay, so what I want to do is to point out that we have a standard way of measuring masses by what we might call the old way. If we have an unknown mass on a balance, then we put known masses on the other side of the balance until the balance balances. So that's the standard way of measuring mass, and I'm sure many of you have done this many times in your education. Now, the problem with this is that these standard masses suffer from the same kinds of problems that I told you about with the kilogram, and so we might want to imagine a different way of doing this. So one different way of doing that would be to use an electromagnetic force to balance the gravitational force of this unknown mass. How will we do that? Well, we get some magnets, illustrated here. They produce some magnetic field, which is indicated by these red lines of force. And then we have a coil that of wire that can carry current. And when we put current through this wire, that current is acted upon by the magnetic field to produce an electromagnetic force that we can balance against the gravitational force. But here's the problem. That, in order to know what that electromagnetic force is, we have to know not only what the current is in this coil, we have to know exactly where it goes. That is, where the current goes in all the wires. And we have to know exactly the value of this magnetic field and the direction in which it's pointing. And those things are very difficult to know. And that's why this simple idea isn't a substitute for measuring things in the old way. But because of Kibble, there is a solution. We take that coil of wire, and what Kibble says is, imagine that we take the leads of that coil of wire and connect them to a voltmeter. And now we move this coil of wire in the magnetic field. And just as when you move a coil of wire in any magnetic field, it generates a voltage. This is what electric generators do. That's what will happen here. And we can measure that voltage using some voltage measuring device. And we can also measure the velocity of this coil. And what Kibble taught us was that if we do this experiment, which we call the velocity mode of the experiment, measuring the velocity and measuring the voltage, we will get all the information that we need in order to use this electromagnetic force way of measuring mass. And so that's what we do. We move the coil at a certain velocity, measure it, measure the voltage that we get when we do that, and then we do the other experiment that we've already talked about, the weighing side of the experiment, where we put a certain amount of current. We measure that current, and we measure what current is required to balance the gravitational mass on the other side of the balance. And that's what we call the weighing mode. Now, how does that work? How does it give us the mass? Well, this equation explains it. This is the mass of the object. When we multiply that by gravity, it tells us the force that we have had to apply in order to balance the gravitational mass of that object when we did the weighing mode. We multiply that force that came from the weighing mode times the velocity that we got from the velocity mode. And that has to be equal to the current that we used when we made the balance during the weighing mode times the voltage that was generated in the velocity mode. Why do these two things balance? Because mechanical power, which is force times velocity, has got to equal electrical power, which is current times voltage, in any proper system of units. So mechanical watts have to equal electrical watts, and that's why this is sometimes called a watt balance. So we solve the equation for mass, and we find that the mass is equal to current times voltage divided by the acceleration of gravity times the velocity. But now you may ask, wait a minute, you promised that Planck's constant was going to be the thing that allowed us to use this procedure to get mass. So where is Planck's constant? And the answer is that Planck's constant comes in because of the way in which we're going to measure the current and the way in which we're going to measure the voltage. These two gentlemen standing next to me at a meeting a few years ago, Brian Josephson and Klaus von Klitzen, came up with wonderful new ideas for measuring electrical standards. Josephson said that if you had two superconductors separated by a thin insulating layer and you apply a voltage across it, that there will be an alternating electrical current flowing between the two superconductors, and that the frequency of that will be given by this constant, 2e/h, whose units is hertz per volt. So that means if we measure the frequency, we know what the voltage is because of Josephson's effect, and the number we plug in is 2e/h. What von Klitzen showed us was that in certain kinds of two-dimensional semiconductors, that the ratio between the current in one direction and the voltage generated in another direction was equal to this quantity that we now call the von Klitzen constant, which has a value of h/e², which has the units of ohms. So you see that h and e appear in these equations, and what happens when we measure the current and the voltage in this way, that E cancels out, and we end up with something that's proportional to H. Now, that's not the only way of realizing the definition of mass using a defined value for Planck's constant. And that's one of the beauties of defining the kilogram by defining Planck's constant, is that it doesn't tell you how you should do it. This photograph illustrates one of the things that goes into another way of getting to the kilogram from Planck's constant. What is shown here is a nearly perfect silicon sphere made at the German Standards Laboratory, the PTB. This is, in fact, the most perfectly spherical object that has ever been made. And by measuring its size very accurately, and by measuring the lattice spacing between the silicon atoms in this nearly perfect crystal, you can determine the number of silicon atoms. By making other kinds of measurements, you can determine what the mass of a silicon atom is, and that means you know what the mass of this object is. But in order to do that, you need to know what Planck's constant is. And since we have a limited amount of time for this talk, I'm not going to give you the details of that, but I encourage you to ask me about it if you're curious about how a manufactured silicon sphere, along with a definition of Planck's constant, can lead to a realization of the kilogram. So, as I told you, each one of the base units of the SI is now defined by assigning fixed values to constants of nature. What about the other ones? Well, we've just talked about how the kilogram is defined by defining a value for Planck's constant, and using that Kibble balance, we saw how it was possible to measure the mass of some unknown object. It could be a platinum kilogram, for example, measuring the mass in new kilograms of that object, and that's how it's done today. We now have a new value, or I should say a new definition of an ampere. You may remember that the old definition of the ampere is that it's the amount of current that when you put it through a pair of wires a meter apart that are infinitely long, that you get a certain force between the wires, 2 × 10⁻⁷ newtons per meter of length of the wires. Well, that's no longer the definition of the ampere. We now define the ampere by defining the charge on the electron. And so the ampere simply becomes a certain number of electrons per second. Now, it turns out that's not the way we actually measure it. Just as in the case of Planck's constant, we don't weigh photons, but by defining what the electron charge is, we can use other techniques, and please ask me about them if you're interested. We can use other techniques to realize the ampere. The mole and the Kelvin also have new definitions. The Kelvin used to be defined as 1 over 273.16 of the triple point of water. And now it's defined by defining the Boltzmann constant. So since the Boltzmann constant is simply a conversion factor between temperature and energy, what this definition is telling us that temperature, as measured in kelvins, is simply a measure of the energy associated with thermal motion of whatever atoms and molecules make up a substance. And finally, there's the mole. It used to be that the mole was equal to the amount of substance that had a certain number of entities in it that was equal to the number of carbon-12 atoms in 12 grams of carbon-12. Today, it's just a number. We've simply defined Avogadro's number. And of course, as I mentioned before, the meter had already been defined by defining the speed of light. And even though I didn't speak of it in any detail, we've defined for a long time the second to be based on the hyperfine frequency of cesium. And you heard atomic fountain clocks mentioned in the introduction. The hyperfine frequency of cesium is a defined number, and it's been defined since the 1960s, and based on that, we know what a second is. So, with all of these definitions, you might say we have really done what the French revolutionaries imagined as a dream. We've got a system of units that's good for all times, for all peoples, à tous les temps, à tous les peuples. And in celebration of that, and as you heard in the introduction, we had a meeting of the General Conference of Weights and Measures, whose purpose was to essentially ratify this new definition of the International System of Units. And after that wonderful vote, where 60 countries of the world unanimously agreed to this new definition of the SI, this was the movie they showed, and I want you to see it as well.
It took more than 140 years.
Groundbreaking science.
And the agreement from the world's scientific community. At times, it seemed
Impossible.
accurate,
Precise measurements.
anytime.
Anywhere. Kindness. We did it.
Ce l'abbiamo fatta. You have no special. Lo logramos.
Messi abone.
Biz buna nail olduk. Welcome, guys.
Biz bunu жасадық. Het is ons gelukt.
Biz gelmeyelim.
Tasarım.
We gjorde det.
Amerika via. Nismo učinili.
Dokázali jsme to.
Congratulations.
Skandina. Felicitaciones.
Mazalto. Congratulazioni.
State renovisa.
Selamat.
Super.
Parabéns.
Ongera.
Momento.
Anguilla.
Olexolo.
Mabruk. Kapai.
Aniko.
Félicitations. Congratulations.
Well, for those of us who were there, that was an incredibly emotional time. It's very rare that 60 countries around the world will unanimously agree on anything, but we did. And it was a wonderful experience. But is this really the end? Have we really gotten something that is good for all times and for all people? Well, the answer is not quite. And the problem is time itself. As I mentioned to you, the hyperfine frequency of cesium is what defines the unit of time, the second, for us today. We have defined what the hyperfine frequency is. That tells us how long a second is. However, other atoms with transitions in the optical region of the spectrum instead of in the microwave, the way cesium is in the microwave region of the spectrum, around 9 gigahertz, but in the optical region of the spectrum, around 10 to the 15 cycles per second, we now have optical clocks that are about 2 orders of magnitude, a factor of 100, better than cesium. And everyone believes that these are going to get better and that they will eventually replace the current definition of the second with a new definition of the second based on optical transitions in atoms held in optical lattices, which is one of the things you heard was something that was developed in my own laboratories. And so we anticipate a new definition. Here's a picture of Junyi in our NIST laboratories, who's getting accuracy on the order of 2 times 10 to the minus 18 instead of around 2 times 10 to the minus 16 for cesium. Here's Dave Wineland, who's got accuracy better than 1 part in 10 to the 18 for these optical clocks. And it appears that even when we have a redefinition, that in the end, it really won't be the end, because regardless of which atom we choose, it may be that future developments will produce time standards that are even better than whatever choice we make to redefine the second sometime, I'm guessing, within the next decade. For example, let's say that we decide to define the second in terms of an optical transition in an atom like strontium. Then 10 years later, somebody learns how to measure the frequency of a gamma ray transition in a nucleus, and people are working on this. And because that transition is even more narrow than the one used in strontium, it becomes a better way of defining time. And then again, we decide that we want to change the definition. And so it doesn't appear that time is going to be something that gives us a timeless definition. And how this definition of time will sort out, well, only time will tell. But for now, we have a really excellent international system of units, and I will be very happy to take your questions.
Professor Phillips, for the interesting talk. As you heard, we have a very fundamental systems of unit now that will link quantum measurements to macro scale measurement. So I think that's very, very exciting. We saw some very clever experiment described by Professor Phillips in realizing the kilogram. Is also the definition of the new definition of the SI is indeed a brilliant method that the metrologists or measurement scientists have come up with. So as we are speaking, quite a number of questions have come out in the chat box. The first question that I have here is on the new SI that is based on the fundamental constant. So are we sure that these constants are really fundamentals and they do not change?
Okay, well, that's a wonderful question. There are really 2 questions there. One is, are the constants fundamental? And then the other question is, do they change? Of course, what constitutes a fundamental constant is really a matter of taste. So, for example, I think that Planck's constant and the charge of the electron are really fundamental constants, but that the hyperfine frequency of cesium is not a fundamental constant. So I try to be careful when I say that the new SI is created by defining the values of constants of nature, not to say that they are fundamental constants of nature, because in my opinion, they are not all fundamental constants of nature. And the fact that the cesium hyperfine frequency is not fundamental is one of the reasons why it's probably not going to be the final definition when we define the second. For example, the Rydberg constant would be a fundamental constant. The trouble is that we don't know how to do spectroscopy well enough and understand the physics of, for example, the hydrogen atom, even the hydrogen atom, the simplest atom. We don't know it well enough. So that's the issue about whether things are fundamental or not. Now the question of whether they change. My opinion of this, and I believe I'm right, but not everyone agrees with me. My opinion is that it doesn't even make sense to ask whether a fundamental constant that has units changes. You see, we use the speed of light to define the meter. What would it mean for the speed of light to change? It would mean that what we mean by a meter changes, but we've defined the speed of light. So the speed of light can't change. Now, to make that more clear, what about constants that don't have units? The fine structure constant is one of those constants that does not have units. It's a dimensionless constant that tells us how strong electromagnetic forces are compared to other forces. If that changes, that makes sense. It makes sense to talk about whether the fine structure constant changes because it doesn't have any units. It's not based on a system of units. You see, saying that the speed of light changes is asking a question that's based on something we made up. We just made up the system of units. But nature gave us the fine structure constant, and we can't do anything about it. The fine structure constant is the same in every system of units, but the speed of light is different if we change the system of units. So let me give you another example. Before the 20th of May, 2019, if someone had measured that the fine structure constant changed, then they might ask, well, which constants that go into the fine structure constant are changing? The fine structure constant is E squared over 4 pi epsilon naught h bar c. Okay, that's the value of the fine structure constant. Well, at that time, epsilon naught was defined, c was defined, so that meant that if the fine structure constant changed, it must have been E and or H that changed. But after the 20th of May, E and H were defined, C was defined, but epsilon naught was no longer defined. So after the 20th of May, if someone asked you, well, what constant changed when the fine structure constant changed, you would have said it was epsilon naught. But now you see how silly that is. If the date on which you ask the question changes your answer, then it's not a question that really makes sense. So I hope that gives you a sense of why we shouldn't ask whether those constants change. We should only ask whether things like the fine structure constant or the ratio of the electron and proton mass, whether those things change.
Thank you, Professor Phillips. We have another set of questions that relates to the silicon sphere and the realization of the kilogram with the silicon sphere. So the first question is the silicon sphere stable? You know, does the surface not oxidize?
Yeah. So the answer is that the surface of the silicon sphere suffers from the same kinds of things that other surfaces do, and so when you use it as a mass standard, you have to think about the same kinds of things. Now, I'm not enough of an expert to know what the relative difficulty is for a silicon surface compared to, say, a platinum iridium surface. But I'm guessing that the perfect crystal nature of the silicon compared to the alloy nature of the platinum iridium makes it easier to figure some of these things out. And that's one of the reasons why one prefers the silicon surface. You can study that surface very carefully using all the techniques of surface science because it's a perfect crystal. Of course, there's surface reconstruction that you have to think about, but But as I said, I'm not an expert, but those kinds of things are definitely issues that people think about when they use the silicon sphere as the way of realizing the kilogram. And the beautiful thing is that the two methods agree with each other. That is, if I measure a platinum iridium cylinder using the silicon sphere method, and if I measure it using the watt balance method, I get the same answer.
So there's a follow-up question on the silicon sphere. How does the Planck constant come in, and then how is it linked to the kilogram?
Okay, okay, here. I think this slide will show it. Now let's see. I have to figure out how to share my screen again. Okay, now are you seeing this slide about mass from Planck's constant?
Yes.
Can you see it?
Yep.
Okay, great. So what what I'm illustrating here is that we have an atom here. Let's say this might be an atom of rubidium, and let's imagine that it could be in its ground state or its excited state. Now I take a photon and send it into the atom, and the atom goes from the ground state up to the excited state if the photon has the right color. But the photon not only carries energy, it also carries momentum. And here's the momentum of the photon. H divided by the wavelength. Now we can measure the frequency and therefore the wavelength very well. So because the atom has to absorb the momentum of the photon, it's now moving. And the velocity at which it's moving is Planck's constant divided by m times the wavelength of the light. And we know what Planck's constant is. We know what the wavelength is. We can measure the velocity. That means we now know what the mass of this atom is in kilograms because of Planck's constant. Now, if I know what the mass of a rubidium atom is in kilograms, and I can compare the mass of rubidium to the mass of silicon, and there's ways of doing that, then I can know how what the mass of the silicon sphere is because of the fact that I can count how many atoms there are in the silicon sphere. So does that answer the question?
Oh, I think that's a pretty good explanation there. We are a bit running short of time now. Perhaps I can ask one more question, and then the last bit would be a bit of advice from you. So what is the importance and the impact of this change of the SI unit to people, laymen in the street, and also the scientists?
Yeah. Well, for the layperson, we hope that it has almost no impact at all, because we have very carefully tried to choose values for Planck's constant, for the charge on the electron, and these other constants that are as close as we could measure them to what they were before we defined them, to the best measurements we made of that. So what that means is that unless you are capable of measuring these fundamental constants as well as the best laboratories in the world can measure them, you won't notice the difference. No one, in fact, should notice the difference within the uncertainties of the measurements. Now, in the long run, it's going to make a difference for scientists, because what it means is that the definitions that we have will no longer be subject to changes that are uncontrolled. Before these redefinitions, the kilogram, the definition of the kilogram was changing in a way that we didn't understand and that we couldn't control. That will not happen anymore. And another wonderful thing is that it used to be, before the redefinition, that we in fact had two different definitions of electrical units. The SI definition and a definition that was sometimes called the practical definition, that was based on the GYSS effect and the Van Klitzen effect. And now both the SI and the practical definitions are based on the same thing. So we don't have this unfortunate situation of having two different kinds of electrical units, something that was evident to anybody who was making measurements at the level of a part in 10 to the 7.
Okay.
That's not very many people, but for the people who do it, it's a big difference.
Yeah. Thank you, Professor Phillips, for your interesting talk and inspiring talk, and also the many engaging questions that the audience has posed to us. But we cannot answer all the questions. Perhaps if you are still interested to talk to Professor Phillips, you can see him on the small group session this Friday. He will be there, and you can ask him further questions if you like. So I think maybe a quick thought from you, what advice you would have for young scientists getting into science, and what kind of skills and competency they should develop?
Well, I think everyone realizes that if you're going to be a scientist, that you need to study the basic science of your field. For physics, of course, that involves a lot of mathematics as well as physics. But I think there's something far more important. And that is that you need to maintain your curiosity about the way the world works. I think that is the most important part of a scientist's toolkit, is curiosity. And what you should do is maintain that curiosity and then study the things about nature that make you most curious. Study the things that are really interesting to you. If you do those things, then you'll go far.
Okay. Thank you, Professor Philip. I'm afraid we have to close this session, but thank you again very much for giving us this inspiring and engaging talk. Thank you very much.
It's been a pleasure. Thank you.
Bye-bye.
Bye. And thanks for all your help, Thomas.